I'd like to welcome you to today's lunchtime webinar in partnership with AURPO on investigating the unknown. So as always, before we start, I've just got a couple of things that I need to run through. The webinar will be recorded and added to the SRP's YouTube channel. As always, you can ask any questions through the Q&A box, and then you can also like any questions that have been asked by other people. At the end of the talk, we're going to ask as many questions as we have time for to the speaker, starting with the most liked first. Any that we don't have time to ask today will be emailed to the presenter afterwards, and their answers will be posted for SRP members on our website. If you need to claim CPD points for your attendance today, then email the code to the email on screen to register your attendance. We'll pop that in the chat so you don't need to scrabble to write it down now. And as always, please send any feedback to Charlene if you've got any suggestions for things we can do better, or topics that you'd like to see us presenting, or in fact, if you'd like to present something yourself, if you've got a topic you might fancy presenting on one of these webinars. I've just got to plug joining the SRP. If you're not already a member, there are plenty of benefits that you can get from being a member. They're all on the screen there. And if you want to find out some more information, just hop along to our website and you can get all the details from there. We've got issue 8 of our Radiation Protection Today magazine out now, and we've got a new one coming up soon, hopefully very shortly in the new year coming out. So get this one read first before the next one comes out. And then, of course, in June, I'm sure you've all got this in your diaries, we've got the 7th European ERPA Congress coming up in Liverpool. The early bird rate ends at the end of January, so if you've not already registered, then get signed up now. Hot off the press from a meeting yesterday with the organising committee, the programme is coming along really nicely, and it's going to be one of our biggest and best conferences yet, I'm sure. So without further ado, I'd like to hand over to Oliver Preedy, who's the AURPO Treasurer, to introduce our speaker for today. Over to you, Ollie.
Thank you very much. So it's my great pleasure to introduce Ralph. So Ralph was the head of physics at secondary school at the secondary school level. During the 1990s, he moved into the Education Advisory Service, supporting teachers in science. There he became the RPA for schools in the local authority, and in his words, back in the bad old days when certification was not required. Ralph became a certified RPA in 2004 through the RPA 2000 scheme, and later joined CLEAPSS School Advisory Service as a senior physics advisor and the lead RPA for CLEAPSS RPA body. Ralph is a member of the AURPO Executive Committee and one of the AURPO Strathclyde University course tutors. He serves on SRP's Research and Teaching Committee, chairing it from 2009 to 2016, and he is also on the SRP's Outreach Committee. So without further ado, I'd like to pass you over to Ralph.
Thank you for the introduction, Ollie, and welcome to this webinar on this very grey and grizzly day in West Sussex. The presentation I'm giving today is based on a presentation I gave at the AURPO conference at CLEAPSS this year. This is about figuring out what an unknown legacy source is, one that's been found usually late on a Friday afternoon, back of an old cupboard, and no one's got a clue what it is. And you get the phone call asking for help. So the scope of this webinar is about getting the information you need to figure out what the source is, to characterise it, quite often for disposal, but maybe for putting it back into use. Now, I'm not going to cover the radiological protection issues or cover aspects of IR 17 or other regulations, simply because there won't be time in the hour slot we've got here. They're equally important, but perhaps for another day. I've had to deal with many unknown sources in my life as an RPA, more than I care to remember. And I've developed my 10 steps, which come from my practical experience, on how to deal with them. It's like an aid memoir, if you like, and certainly some thoughts on the instruments that you need to help you identify and characterise the source. I'll say at the beginning, it's worth keeping a record for future finds, if not for you, then for colleagues. So often you find something and then the knowledge gets lost in the history of time. And that's something we do at CLEAPSS and CERC. We've identified currently well over 70 sources that we found in schools. These are from old school educational suppliers where the information has gone missing And we can quite often, in about 3/4 of cases, identify what the unknown source is from the evidence that we've collected. That's photographs and measurements that we've made. So if you do ever find yourself in a situation where you've got to identify an unknown source, do think about keeping a record. Other information is available. This is one I found. It's the IAEA Nuclear Security Series number 5. It's a very good read, actually. A lot of photographs and pictures, mainly of HASS sources, but there are also some lower activity sources. And it very much focuses on identifying the source, not about on characterising it, but nonetheless a use of resource if that's valued in your sector. Step 1. Never underestimate the human capacity for naivety, folly and skullduggery. So on the left, you can see a picture there. I was called to look at a store cabinet that reportedly had 2 grams of radium paint. You can imagine my concern. As you can see there, it says CLEAPSS, which is German for light paint, blue-green. When I investigated and looked at the can, and bearing in mind the concern I had, 2 grams of radium paint, the significance for contamination and the beta field you can get from it, very worrying. When you look on the left, you can see that some numpty has scratched out the word nicht, which is German for not. And on the right, you can see a photograph of the pot as it was sold. Someone has decided to scratch out the word not and put it into the radioactives cabinet. So be aware of this. In my experience, people can do some very numpty-ish things which can cause confusion. 2 more here. On the left is a flask, which is the typical green colour with the radioactive label on it. In fact, it wasn't radioactive at all. I suspect it was a solution of some nickel compound, probably nickel nitrate, to give that greeny colour. My guess would be it was a prop for some drama made by the science department, and they probably kept it for future use. And of course, over time, the information gets lost and no one knows what it is when they clear out the cupboard. And on the right is a castle, it's a lead castle from any technology, and this is quite common. People stick a trefoil on equipment that's part of the radioactive kit. It's not radioactive, but it belongs with the kit for radioactivity. And people forget that, and they assumed, rightly so, later on that it's radioactive. In fact, this wasn't at all. Just a case of removing the trefoil and disposing of it. Step 2. Get them to do some work. You're not the cavalry. There's a temptation. I've called the RPA, stand back. So I get them to take a photograph. And then again, if you've got something like the Source Spotter's Guide, which we have, often you can recognise what it is, and that solves the problem. If they're worried, then use a selfie stick or something else. The key bit here is to have some scale to it, so a ruler in the background's handy, and a sharp photograph. I cannot tell you the number of times I get a camera that I swear has been taken with a box brownie from 50 metres by someone with very shaky hands. No use to me at all. On the left there you can see it's a bag, and I can recognise it immediately. It's a plastic bottle with a little tube. That's an old 1960s thorium carbonate thoron generator used for measuring half-life. And we know that these bottles become very brittle and they split, and then you puff a flour of very fine thorium powder out. They're quite hazardous. But we know what it is, we know how to deal with it, we know a disposal route for it. On the left, when I had to deal with, I had no idea what it was, but it gives you some idea of the size of it. On the right you can see it's a bottle, it's a powder, and again it gives you some ideas of what it is, probably a thorium compound. And the key part here is the form of the source is part of its characterization. It's not just the radionuclide and its activity, it's its form, sealed, unsealed, the type of container. Here's a photograph I received, and you think, really? What? Even this is helpful. What's it tell you? Well, it gives you some idea of the size. And secondly, it can tell you that people who did it haven't got a clue what they were doing. This idea, if you wrap something in lead, it kills all radioactivity. that tells the people dealing with it needed training at the very least. 1 millimetre of lead is not going to stop most gamma radiation. And then ask them for some clear analytical information. I sometimes get schools, they ring me up and say, well, I've got a source that's 200 becquerel. But on question, I find they'll actually mean 200 counts per second. They conflate counts per second with becquerel. So I discussed with them what detection kit do they have, what competence do they have, what's a suitable distance, and then with your equipment, take some counts over 100 seconds, say, with a shield, an aluminium or piece of wood will do the trick. 10 mil of wood kills most beta. So with or without the shield. And that again starts to build a picture to get some idea of what you're dealing with. Step 3, push. And I'm really being pushed for as much data as you can get from other clues. So when they say that Professor Selmo, it was his source and he left 2 years ago. Well, you get onto the HR department and say, can we contact Professor Selmo, who left this with this present? If we can contact him, we can get some information. Any old delivery notes, any numbers or catalogue numbers on the box, any other equipment lying around near it that gives you a clue that what it was used for. Where was the source located in the laboratory? All these things start to build up a picture. Get them to search and search thoroughly. Don't accept we don't know. Have a thorough look. It's amazing what then turns up and helps you build a picture of what the source can be. Okay, so you can't recognise it from the photograph. You have to turn up and do some measurements and help the organisation. Step 4, and I think this is one where often people forget. Agree your terms and conditions beforehand. Agree the working space you're going to have. You don't want to turn up to a laboratory that's full of clutter and no space for you to work in. The entry restrictions. Have you got people who can just wander in and wander out? And I would suggest you seriously consider setting up what I call a temporary supervised area. And I certainly tell the senior leadership team of the organisation that's what I'm going to do. And that then controls who enters and exits that space whilst we do the investigation. I've had incidences way in the past where I've been working on something, but a clear notice up, do not enter. And then the deputy head wanders in, starts asking questions until I shriek at them to get out. So you've got a definite controlled area. Often I have a technician standing by the door to control who comes in and comes out. You don't want people just wandering in whilst you're doing the data collection. When you turn up, you also want to make sure you've got the key holder. I don't be rooting around for the key to the store cupboard. So I can go in, get to the source so we can start the work. And the other things, what they're going to provide and what you'll provide. And 2 other key points here. I warn them, I may not be able to identify the source. I might have to come back or might have to give up. I've never had that situation where I've failed to identify a source, but who knows? And secondly, I'm not going to take the source away. They often think I'm here, I'm going to collect it from them. No, it's your legacy, it's your responsibility to dispose of it legally. And the last one, parking. Don't make me walk a kilometre down the street to the school with all my kit, because the car parks, which often are absolutely ram-packed, I want a reserved space close to where I need to unpack, take my kit out and do the measurements. Step 5. In all this, don't overlook the radioactive hazards. Do you have to work in a confined space if they can't get the source to a laboratory? Are there members of the public nearby who could wander in? What about the chemical form of the radionuclide? For example, we often get uranyl zinc acetate cropping up. It was used in the 60s as a test for sodium, because it's one of the very few sodium compounds that will precipitate out if you react it with uranyl zinc acetate. But it's also a very fine flour, and it is very chemically toxic. So it's not just the radiotoxicity, it's the chemical toxicity that you have to be aware of. So keep in mind the other hazards besides the radioactivity. We get so focused on looking at the radioactive hazards, we forget sometimes about the other things. Step 6, the bad news. You can't do it with a ruler and blue tack. You need the right detection kit. There's no way around this. You need the kit. And at the very minimum, I would say you need a contamination monitor, a rate meter. And if that's a count facility, that's also very useful. A beta gamma dosimeter and a gamma spectrometer. And I'll develop my talk through this in the next few slides. And you can't give someone the wrong kit to identify what the radionuclide is. You have to have the right kit. But that said, you don't need the latest or singing or dancing equipment. You know, old analog equipment that's well maintained in good working order is absolutely fine. My go-to contamination monitor is a Mini Instruments 900E from the 1990s. It's maintained, it's calibrated, it's a grand piece of kit that does the job, and I know its foibles and what it's good for. And that's the other point. Do you know the limitations of your instrument? And it's often buried away in the back of the manual or the specification sheet. It doesn't stick. It's not a label on the side of it that tells you what its limitations are. And the bottom line is, if the piece of kit can't tell you what you need to know, it's no good to you. Okay, how flash it is, or what things it does, if it doesn't read the data you need, it's no good to you anyway. And then contamination monitor. Again, my 900E, it's other bits of kit like the Radii B20s, that was a fabulous piece of kit. Very good for getting an initial qualitative idea, sort of measure. What are you dealing with? You know, is there any contamination in the extent of it? So that with a dosimeter are my sort of first instruments I use to get an idea of what's going on. But to identify the radionuclide, we're often down the road where we need to look at the photon emissions. So it's worth me talking about that for a few slides. Now, I'm sure most of you know this, so a quick recap. After the initial change in the nucleus, where you get the proton number changing or the neutron number changing or both, the nucleus is left in an excited state, and it de-excites by emitting gamma radiation and often X-rays too from changes in the orbital electrons. And the energy spectrum, and I emphasize that, it's the spectrum of the gamma and X-rays that's unique to the radionuclide, not a particular energy, it's the whole spectrum. And there's several databases. The one I tend to use a lot is the Brookhaven National Laboratory. And if you Google NuDat3, it takes you straight to it. It's got all the data of the spectra of the radionuclides. And I picked up a couple here, CZ137. So we've got a prominent peak at 61.7. There's another peak down here, much lower. There are others too, but they're too small to be seen on this chart. And americium, there's a prominent one at 59.5 kV, another one at 13.9 kV, and other ones, again, too small to be seen on the chart. And if you've got those two and very little else, that is an indicator you've got americium-241 and not any other radionuclide. Now, you can't measure energy directly, so derived quantities. You have to measure it from other measurable quantities. The way we do that is, by the way, it interacts with material. And there are three ways in which photons interact with material, what I call oof, and what. You may call them by other names. That's what I call them when I'm teaching. Now, the oof is when a photon hits an atom and all the energy is completely released into the electron. The electron's energy then is a proxy for the photon energy. Tiny bits lost in being released from the atom, but most of the energy in the electron is all from the photon. That's the one we want. That's the key to measuring the photon energy. Of course, it's not simple like that. There are other mechanisms where you get the so the photon comes in, it deflects, and some of its energy, but not all, is released as an electron. And the kinetic energy of the electron is not representative of the incoming energy of the photon. And the photon changes its wavelength, it's a slightly longer wavelength, and because the probability of interacting with material is low, it probably escapes the detector. So not one we want for determining the energy of the photon. And the last one I call what is when a photon, and it has to be fairly high energy, over 1.022 MeV, comes in, hits the atom and produces matter, an electron and a positron. And students often get, don't understand that. They know the opposite from E equals mc squared. They don't realise the converse is true, that photon energy can become matter. And again, that's not much use to us as a measure of the energy. It's the first one is the best one. Of course, we know them by the more fancy names of the photoelectric effect, oof, Compton scattering, or pair production, what. The way we detect them, well, there are several ways. There's the scintillation type detector, and this is a bit like a solid state liquid scintillation counter. And a gamma photon excites the crystal lattice. When the crystal de-excites, it emits a light photon, which is detected by the photosensitive element underneath there, you can see. And the electrical signal is produced, it's amplified, and then the pulse height is a representation of the gamma energy. So if you measure the pulse heights, you get a measurement of the photon energies coming in. And the crystals there, there's the sodium iodide, the doped sodium iodide is fairly been around for some time. There are some newer ones, the GAG-GCE and the cesium iodide doped. And I've noticed there the cesium iodide ones, the price has been coming down quite a lot. These are getting cheaper to manufacture. And the second type is the semiconductor type. This is a bit like a solid state ionization chamber. And that's the gamma photon comes in, it causes whole electron pairs in the crystal, and then you sweep up the charge by applying a voltage and you amplify it. And then again, the height of the electrical pulse corresponds to the incoming gamma energy, the photon energy. And the two there, the hyperpure germanium you'll be aware of, a new one on the market, the cadmium zinc telluride, the CZT, that actually has a much better resolution than the scintillation type crystals. So that's quite exciting in terms of getting a higher performance of measurement. Okay, so you've got the pulses coming in, so you need a pulse height sorter, called by the fancy name of a multi-channel analyzer. Now, so the pulses come in, they're sorted into bins, and then from that you produce a graph. And then you can see your photo peaks. It's really a fancy digital to analog, analog to digital converter. So what about the number of bins or the number of channels that you need? You might think, well, the more the better. Not so. You need enough that matches the resolution of your detector, but the more channels you have, then the longer it takes to get a graph. So if you've got, for example, 1024 channels, it'll take some time to get a decent looking graph. If you've got 8,000 odd channels, it's going to take you roughly 8 times longer to get the same height graph. And if you want to get in and measure something and get out, then higher numbers of channels, bins, is not necessarily a good thing. And for the sort of work we do, anywhere between 1,000 and 8,000 channels seems a pretty good compromise. And you can see there, this is from a radio code gamma spectrometer, which I'll discuss more in a minute. And you can see there the channels, the bins. And often software smooths it out, but you can see that comes from the height represents the number of pulses in each bin. And also an important measure of the quality of the detection is how narrow the photo peaks are, because the photo peaks are always spread. It's because you've got electrical noise and the statistical fluctuations from the involved in the photon to electrical conversion. And the narrower the pulse, of course, the better, because you can get more accurate measurement of the energy of the photo peak. And it's measured in what's called the full width half maximum. And it's conventionally quoted at 661.7 keV. That's the main peak from cesium-137. Be warned, I have seen 1 or 2 cases where they quote it at a different energy, and it's better at lower energies usually. So full width half maximum, a measure of the resolution of the detector. Worse than 10%, not so good. The lower the number, the better. The sodium iodides sort of tend to be around 7-8%, which is fine. The CZTs can be very low, around 2.5%, very good. Of course, the hyperpure germanium, the cool ones, can be very low, 0.5%. Anything more than 10% starts to get iffy in terms of you working out what the energies of the photo peaks are. Okay, 2 gamma spectrometers here. On the left, the cryogenic hyperpure germanium detector. These are big bits of kit. They're fine in laboratories. They're not portable. They take time to set up, and they're not really of much use when it comes to you going out to the field trying to determine a gamma spectrum. On the right, a nice bit of kit we've got here at CLEAPSS, an Exploranium GR135. These are around for some time. The resolutions aren't bad, but they were expensive. I think over £10,000 each. I remember. Not something you can easily go out and buy. But and here I'm really pleased. There's a major change in developments in cheaper room temperature portable spectrometers. And I've listed 5 here. I'm sure there are others kicking about. The 2 I've ticked in green we've played with here at CLEAPSS, the Chromac RA4S. It was £700 when it was on sale. A cracking piece of kit. But unfortunately, Chromac are no longer producing it. I think I need to moan to Chromac, so why? And another one that's new on the scene, it was indicated to me by the late Neil Higby, who pointed it out to me, and I then bought a couple. I have to say, I was blown away by it. It's a blinding piece of kit, and the base one is £180. The top of the range is £350. 3 others that I'm watching, are listed there. Some are not released yet, but again, they could come into play, which means you've got affordable, portable, room temperature gamma spectrometers. And here are photographs of 3 of them. The top one is the Chromac GR1. That's a really expensive piece of kit we've got at CLEAPSS. We tend not to use that for going out in the field. But there's the Chromac RA4S, called the Rad Angel, and these are all the same photographs. You can see the scale, and the radio code 103, and that was retailing at 220. The top 2 have to be used with a laptop. The radio code can be used as standalone, but you can also plug it to a laptop. And they can all export data as a .spe file, a spectrum file, which means you can then analyse it using Excel or your favourite spreadsheet. Yeah, the reality, of course. There are, well, all instruments, none are ideal, and there are problems. So the idea that photons augur up their energy nicely into the crystal, yeah, not a chance. Well-defined peaks above 1 MeV, no, you're pushing a lot. The electrical noise and the statistical fluctuations spread them out. And picking up low energy peaks, beware that some spectrometers have a cutoff, and I know the RA4S cuts off at 40 keV. So if you're looking at lower energy photo peaks, that's not going to do any good. So step 7, you've got to interpret the data, the gamma spectrum. It needs thinking about, because a lot of the information there comes from the physics of the detector, not from the gamma spectrum. Keep in mind too, confounding problems such as decay chains, for instance like thorium, uranium, radium will have long decay chains, and some of those radionuclides in the decay chain are prolific gamma emitters. And X-ray fluorescence, so the immediate container of the radionuclide can emit X-rays, which again can muddy the waters. So looking on the left, there is the data from the NNDC, the spectrum, the theoretical spectrum from cesium 137. Now look on the right, and that's from the high quality Chromac GR1. Yeah, okay, you've got the photo peak here, but all this stuff here, and this comes from Compton scattering. And this you could mistake for peaks, and they're not. It's this it's what you're interested in. So again, you need to interpret the spectrum in front of you. Now the radio code, it has an inbuilt library, and I've got here that I've superimposed the radium library on top of a piece of the radium timepiece I was measuring. So it shows you where the photo peaks are. I say I was impressed by this, and that you can see, and that clearly shows you've got radium, because the library also includes all the decay chain of radium. Okay, well, suppose your piece of kit doesn't have an inbuilt library. Well, other things are available. There's the database from, I think it's from Idaho library. There's the link at the top, and that gives the gamma spectra that's measured with an HPE detector for a whole range of radionuclides. It's an impressive range, and you can see here, yes, the Idaho National Laboratory. You can see here the one that's for radium. So you can look along there and see all the photopeaks and see if it matches your gamma spectrum. There's also one, and this is my go-to, and I have to say, NuDat 3. Again, there's the link for it. It's free. All these are free. If you click on that link and go to decay radiation, it's got a huge data set, and it allows you to do a search. And so here you can pop in, you don't know what the radionuclide is, you can pop in you're interested in gamma, you can put the window of energies you're interested in, you can put something like the intensity between 5 and 200%, because you're not that bothered about really small intensities to start with. I click formatted file because it's quicker, and then say search, and it produces an ASCII file. This is an extract of it, a huge ASCII file of all the elements that are outside the radionuclides that are producing that energy you search for. And there's the one I'm interested in. It's pp214, which is in the decay chain of radium-226. So again, I find that very useful and free. You can try AI. It does seem to have got better. So it really hinges on the question you put in. So you have to be very specific. So here's the question I put in. I put it to Copilot, Gemini AI, and ChatGPT. And I did it a couple of times. And the first few times, Copilot and Gemini AI were just rubbish. I tried it recently, in fairness, and I have to say Gemini AI and ChatGPT, okay, they got it right. It's radon 222, except of course that's not the head of chain, because radon 222 is not a sealed source. It's radium 226, but nonetheless, it's pointing in the right direction. Copilot told me it was barium 133, or possibly cesium 137. I don't know how to arrive at that. So, with caution. AI can tell you wrongly, confidently. Okay. And what happens if you've got no gamma? Bear in mind, it could be that your gamma detector has got the range to measure. There is gamma, but it's not within the range of your gamma detector. There are one or two niche alpha emitters. I think gadolinium 148 is an alpha only. Polonium 210 is also nearly an alpha only, but it's such a short half-life that it's not going to be applicable to a legacy source. So it's more than likely you've got a pure beta source here. Okay, you've got a pure beta source. The ones in yellow are unlikely to be the ones you're dealing with as a legacy source. They're short, the half-life is too short. Now, the range, of course, is affected by the container, but it serves as a lower limit. So if you detect beta if you detect beta at a meter, it can't be carbon-14. So it really does limit the beta radionuclide that it could be. And also the form. For nickel-63, it's going to be more than likely electrodeposited metal. Carbon-14, it's going to be more likely an unsealed source, either in tablet form or liquid form. On the right here are ones that I've actually come across in my investigations of unknown sources. So starting top left, that's a carbon-14 tablets. Then you've got little chlorine-36 test source for liquid GM tubes. Bottom left, this was the thing that was hidden by the lead wrapping I showed you earlier, is a 720 megabecquerel beta voltaic source. And then you've also got a nickel-63 source from a gas chromatograph. Detecting tritium, well, we know tritium is notoriously difficult to detect. You can't pick it up with a geode tube, but possibly bremsstrahlung. And I tried a little beta light source, a gaseous tritium light source, 12 gigabecquerel, with the irradia code. I have to say, I was surprised. You can see there the two graphs, background, and then with the radia code, and it's picked up the bremsstrahlung, and you can see the maximum there at 17 keV. So I could identify that as being tritium. The cutoff point for the radia code is about 9 keV. I would say for a cheap device like this, I was absolutely impressed with it. I have no shares in this company, but I have to admit it was a good piece of kit. Okay, step 8 then. Okay, so you've identified the radionuclide. You now need to get some idea of what the activity is. So there are several ways of doing it. I think the way I tend to go for is the dose rate. So measure the dose rate at a fixed distance. Either you can use the specific gamma ray constant and calculate it, or my preferred way is to use RadPro or VARSkin2 backwards. So in VARSkin, it's actually meant for skin contamination, but it will do HP10. So if you put the dose steps to 1000 milligrams per centimeter squared, set the exposure time to an hour, so that'll give you the dose rate, set the averaging area to 1 square centimeters, and set the air gap to how far away your dose meter was. VARSkin is set at maximum of 20 centimeters, but I found it does still work at 30-40 centimeters. Then put in 1 megabecquerel, and then that gives you the dose rate for 1 megabecquerel. So then from that you can figure out backwards what your activity is. Same for the beta emitter. Again, of course, you've got there the problems of the container. But again, with VARSkin, you can make some estimates of the container. You can put it into, using covers, you can put in the container, but the dose depth there is 7 milligrams per centimeter squared. Again, put it in for 1 megabecquerel and look at what the dose rate is, the beta dose rate. So that gives you an upper limit of what the activity could be. There is another technique which you could use, and that's from the bremsstrahlung. There is an equation which tells you the dose rate from bremsstrahlung, and I found a very good book, but it's annoyingly out of print. I mean, other books are available by McClintock. This book does float around in the radiation protection community, so if you can get hold of a copy of it, it'd be nice actually if we could get it reprinted. That gives you the information which will help you work out the dose rate from the bremsstrahlung, and hence the activity. Okay, don't forget you've always got others in the community. So that device here, when I found it, I didn't know what it was, and I contacted several RPAs, one of which was Sheila Liddell, and she knew exactly what it was. It came from an old 1960s electron microscope, and they used the beta source inside in a vacuum tube to generate extremely high voltages, and the little ceramic thing on the top there gave away that it's high voltage. So I was able to identify it, characterize it, and then arrange disposal. Another one which a colleague of mine from Imperial identified was something from the 1930s, I think. It was a little piece of radium that glowed in the dark, and you put on your car key, so you could identify your car. And there's the advert for it. So again, ringing colleagues can help. And coming to the last step now, and probably arguably the most important step, know when to call it a day. If you haven't got the kit, it's becoming the situation's becoming too iffy. Stop, walk away. Under pressure, you can be pressed to identify it. Don't. You don't know. You need to go away, think about it, and maybe come back another day. So don't endanger yourself or the environment, and don't go off piste with other techniques. When you come to the point you can't go any further, stop. So that's the 10 steps that I use. That's a summary of them. I hope you find them useful. Those on CPD today, I think those regulations are relevant in my presentation today. And I'll leave that for a second too. There are the QR codes for the websites that I've spoken about today. So if you've got your phone handy, before I remove this screen, just click on it. So that brings me to the end of my presentation. I hope it's been useful. Don't forget, these are my 10 steps. Please feel free to adopt, adapt, amend as you see fit that fits your sector. Thank you for listening.